That's not a big deal. Okay? Really what I want to get back is our chemical and physical properties. Okay? Which should be a review for you guys because you did a lab on chemical and physical properties. That was like the first lab, and it was easy, right? Yeah. Okay. Chemical and physical properties is actually a very challenging topic to deal with. Okay? So it becomes difficult for students to kind of process at the very beginning of their chemistry careers. Most chemists find it all obvious because we've spent 20 years doing it. Okay, so we recognize those differences. So our physical properties are observable characteristics. Okay, they don't alter the elemental composition. Well, we have some context now of what elements are. So if I look at a compound of water, I know 2 hydrogens and 1 oxygen. If I somehow change that to now 1 hydrogen and 1 oxygen, have I altered the elemental composition? Yes. That's now not a physical characteristic because I've changed the elemental composition. Okay? Phase transitions, sometimes color, density, solubility, conductivity. Those are things that tend to be physical properties. Chemical properties describe how a compound changes when we change the bonds within it. So when I have water and I change it to OH or HO, depending on how you want to look at it, have I changed the chemical properties? Well, if I splashed water in your face, you probably don't care. If you somehow got OH splashed in your face, first off, more than likely, it's not a splash. Okay? It's actually a bunch of solid pellets hitting you in the face. That's a pretty significant difference. Okay? Add to that, let's say we put it in water so it was in the liquid phase, it would probably melt your face. 1 atom. That's a pretty big deal. Okay? So we want to be able to acknowledge some of those differences between the physical and chemical properties. Chemical properties are always how it interacts with something else, like your face. Okay? Or other materials if you don't want to splash stuff in your, you shouldn't splash stuff in your face. Don't do that. Okay? Some people are laughing. Please don't do that. Like that's legitimate. Don't do that. Okay? So how could we potentially go through and look at these? Okay? So we can look at then chemical and physical changes. The changes tend to be a little bit easier to go through and interpret. Okay? Sort of. Okay? The properties are kind of challenging. The changes we can see with a chemical property because the chemical property said what happened when we mixed it with something else. So by definition, a chemical property is hinging on a change. Okay? So a physical change, like melting ice, okay, or boiling water. What happened when I melt ice? The basic level. Solid to a liquid. Okay? How did it transition from a solid to a liquid? You added heat. So for that phase transition, you supplied the energy to cause the phase transition to happen. What if you didn't supply the energy? And so that's where it becomes weird because we think about ice. Well, if I put ice on the counter, I'm not supplying any energy, but it's still transitioning to a liquid. Did you supply energy? You did.
Put it up there.
You placed that object, ice, from a 0 degrees Celsius place to a 20 degrees Celsius place. You did supply energy. That energy was just the temperature change of the room. Okay? So you did supply energy to that. What if I take that ice and I leave it in 0 degrees Celsius? It stays the same. Okay? What if I took that liquid stuff that started to come out of it and I put that back at 0 degrees Celsius? Have I applied energy? I've removed energy from the system. I've absorbed that energy away from it. Okay? So these are now reversible processes. I can either add energy in or take energy out. If I'm the one manipulating the energy, that's a physical change. Okay? What happens with a chemical change? Okay? During a chemical reaction, we form a new substance. How would you know a new substance was formed?
Reaction.
A chemical reaction. How would you know a chemical reaction has happened? Okay? we could look for evidence of chemical reactions. Color changes are evidence. Changing in phase, okay? The formation of a gas, a solid, a liquid. All of those are examples of a chemical reaction. Okay? An energy change observed. Those are examples of chemical reactions. Your textbook has listed gases, formation of gases, and I think formation of solids as two separate things. I would argue that's just a change in phase, so that 1 and 2 are the same concept. Okay? So let's immediately apply these rules, because this is awesome. I take that block of ice, I put it on the counter, what happens to it? It melts. It becomes a liquid. Did I change phase? Yeah. So that's a chemical. 5 seconds ago, didn't I just say that was a physical change? Okay. These aren't clear-cut, obvious things. Okay. What causes a chemical change versus what causes a physical change? A physical change tends to be something initiated by you, the chemist or the student. Okay? A chemical change, I take two liquids and I just mix them together. Okay? I just put them next to each other. Poof, a gas forms. Did I get a change in phase? Yes. Okay? How did I transition from a liquid to a gas? What do you have to do to go from a liquid to a gas? In general, what do you have to do to go from a liquid to a gas? You have to add heat. To boil, to get water to go to the gas phase, what do? Put it on the stove, I add heat. Boils and becomes a gas. Okay? Did you add heat when you mixed the two liquids? No. Where did the heat come from to make the gas? If it didn't come from you, it had to come from whatever was in those liquids, which means the chemicals supplied the energy. If the chemicals supply the energy, it's a chemical reaction. Okay? Permanent color changes. This one's difficult. I take food coloring. I add it to frosting. Okay, white frosting, right? What color does the frosting become?
Food color.
Food color. Good hedge bet there. Okay, I add red food coloring to white cake frosting. Okay, it might start kind of barely pink, and then as I add more, it becomes more and more red, right? Okay, is that an easily reversible process? Not really. Okay. Turns out there's actually studies that you could theoretically reverse that. Theoretically. Okay. It's not very easy, but you can prove that. Okay. When we're looking for a chemical reaction, it's a permanent color change. Okay. So with the frosting, when you stir that in, if you go through the exact same motions of that stirring process, you will reverse the color addition. Okay. There's studies that actually prove this. Okay, it's not easy to do with frosting, okay, but you can pull it off where you exactly reverse the process. For a permanent color change, I mix two clear liquids. Okay, notice that this solution in the beaker, Erlenmeyer flask, is clear, and in the dropper is clear. When they mix, what happens? A color change. Why did it change color? Both of those were clear. This is not a dilution of color. I started clear. Now it's yellow. What caused the color change? A chemical reaction. Okay? So we're not looking at a dilution when we're talking about color change. The other one is an energy change is observed. Okay? So another tricky one, I take my pot of water, I put it on the stove, I turn on the stove. What happens to the temperature in the water? It rises. Temperature changed, didn't it? So that's a chemical reaction. No, why not? What caused the temperature to change? Me. I added energy to it. I'm the one causing it. That's physical. Okay? I take two liquids, I mix them together, and the solution gets hot. If those were room temperature liquids, where did the energy come from to make the solution hot? The chemicals, that's a chemical change. Okay? Kind of makes sense? So in that lab, they talk about reversibility and irreversibility. Okay? I really hate that reference because it's wrong. Okay? I can take water and turn it into hydrogen and oxygen. By that same token, if I take hydrogen and oxygen and light a match, they turn into water. This is why we have hydrogen fuel cars. Okay? That would suggest both of those are now physical changes because they're reversible. No, I changed the chemical nature. Those are chemical changes. So the idea of reversibility tends to be one more of easy. Was it easily reversible? Okay, that's physical. Is it hard to reverse? That's chemical. Okay. Why is that definition also a pain? It's a subjective observation of easy and hard. Okay, so be careful referencing reversible and irreversible with chemical and physical changes. They're talking about ease of doing it. Okay? And that's one of the things that I find kind of difficult within chemical and physical changes, because ultimately we discuss it as black and white. It is chemical or it is physical, and there is no gray area. It's not. Chemical and physical is actually a spectrum. Depending where we fall on that spectrum, we might call it physical or we might call it chemical. For instance, melting ice. That is strictly physical. Okay, so I would argue that that would be our red physical. How about dissolving sugar? Dissolving sugar is physical. When I dissolve sugar, I do not break the structure of sugar. I do not break the structure of water. All that happens is I get them to mix evenly with each other. I form a homogeneous mixture. Burning wood. Did you apply the heat to constantly burn the wood? No. You supply the heat to get the reaction to start. Just like when you mixed two liquids. When they were separate, they didn't form a new phase. You had to mix them. There is still an energy involved there. And some reactions have a larger initiation process. Burning wood becomes a tricky one because if you've ever tried to start a fire, okay, like a little camp stove fire, not the camp stove fires, those are easy. If you try to start a wood fire, those become a little bit more difficult. Okay, you'll get some people say, I can't start a fire, and some people are like, yeah, let me do it, because I can get a fire going real fast. Okay? And then we usually point and laugh at them when they screw it up. Right? Yeah. So it takes a little bit of effort to get the fire started, but once it's started, it self-sustains. Why is it self-sustaining? It's providing constant energy to keep the reaction going. Okay? So it is a chemical reaction. Okay? We're going to skip dissolving salt for a moment. Mixing red food dye with white cake frosting.
Physical.
This is physical. We just discussed this, and I did say that we could reverse it. Interestingly enough, it was my dad that talked about this. It was really bizarre. Totally side consequence thing. I'll see if I can't get that demonstration set up so we can actually see that it is indeed reversible. Okay? Because it is kind of neat. I've been told that you can do it. I don't know if it's actually true or not, but I've been told. What's happening in the bottom one? So we have A, B, C, D, E. What do you see happening? Changing color. Okay? What do you think? Chemical or physical? Okay, chemical. Why? Okay, the crystal looks the same, right? So it changed colors. Okay, so we would suggest chemical. What if I tell you, if I change the color of the light aimed on it, it goes back to being A? Then you would say physical. Guess what? You were right the first time. It's chemical. Okay. How would you know that? Because you've studied the process on why and how that thing is happening. And actually what's happening is it's absorbing energy from light, changing the chemical structure. That change in the chemical structure changes the color. That process is easily reversible, and it undoes that when you remove the light, and it goes back to its original state. Kind of a neat molecule. Anybody seen those glasses that change color in the sun? It's the same thing. Okay? It is a chemical process. You're changing the chemical structure. Even though that is really easily reversible, what did you do? You took away the light. Okay? Very bizarre, but that is a chemical process. Okay? Where would that fall on our spectrum? Well, it sounded easily reversible, so that would sound physical. But I'm changing the chemical nature, which makes it chemical. So that process is probably sitting closer to that green line, because it's more chemical I would actually argue it's probably a blue on our rainbow. Kind of makes sense? Okay, now the fun one, dissolving salt. Right? That sounds an awful lot like dissolving sugar, because sugar is what? Describe sugar, and don't say tastes sweet.
Solid.
It's solid and white, right? That's it. We don't need to get difficult. What's salt? Solid and white. So I'm taking a clear liquid and I'm mixing it with a solid white crystal. When I mix those two things together, what do I end up with? A clear solution, whether it's sugar or salt. Right? So we get the exact same observables. We could add to this, could I get rid of the water? Could I reverse that process? How would I do that? I would evaporate off the water and I'd be left with sugar and salt left over. So those are both pretty much identical processes. So if I said dissolving sugar was physical, what would you expect the answer for dissolving salt to be? Also physical. Nope. It's chemical. How do I know that it's chemical? When I take salt, sodium chloride, solid, and I add it to water, the ionic bond breaks into sodium ions and chloride ions. Both of those are water soluble. What did I do to the bond that connected sodium to chloride? I broke it. What kind of bond was it? An ionic bond, typically also called a chemical bond. Did I break a chemical bond? Yes. By definition, that is chemical. But everything about it was that it was reversible, which is why I would argue dissolving salt sits right dead center in the middle between chemical and physical. And depending on who you talk to and how much chemistry they know and want to apply to the situation, they get different answers, which is very entertaining. Feel free to look at the internet on it. The internet seems to be pretty equally divided. And the chemical people are right, in my opinion. You are breaking a chemical bond.
What do you want us to know?
Right? So that's a good question. Because what do we then get for this class? Do you just come to class and just listen to me talk and you're like, yay, that was cool, that was a fun day? Okay. You're probably like, yay, that was cool, that was a fun day. Damn, I got to get tested on that? Okay. You're concerned primarily about tests. Hopefully you're all saying, yay, that was a fun day. Okay. Some of you are like, what the fuck is wrong with you? Okay. It's a chemical process. How do I then test you on this? Do you think I should give you the ones that sit in the middle? No. Which ones am I going to test you on? The extremes, the far left and the far right. The most extreme chemical and the most extreme physical. Okay? That is not an easy process to go through and do with a test question. Okay? And I have seen the final multiple cases where they don't do a good job separating those questions. Okay? I try my best when I write test questions to fix that, and if I see test questions that don't match that correctly, but after you've taken the test, that's where you come back and say, I think this is a challengeable question. Right? You make your case. You don't just say, this is challengeable. You tell me why it's challengeable because of where they fall on that spectrum. Right? Prove that knowledge, then I would accept it. Make sense? Okay. Good? Okay. So, states of matter and equations. Okay, this was all in that video that you guys watched. Did you guys have questions at all about what you can find in an equation? That all make sense? Okay, so what we're going to do, just to give you an idea, is the titles of these are in red or black. Red means it was in that video, so I kind of just want to move over it. So if you're like, I had a question on that, this would be your opportunity to ask. Okay. This kind of floats back into chapter 3. Okay? During a chemical change, certain things were made apparent. Okay? And so we had some scientists discover things. This is where they come up with the law of definite compositions. Compounds always contain the same elements in a constant proportion, interestingly by mass. Okay? Why would he have said by mass? Okay. Any guesses? What do you think? Is Proust, that's the picture of him, old guy or young guy? Or let's try it this way. Dead guy or live guy? Dead. How dead? Long time dead. Okay? Long time dead, well before the existence of electrons and protons. Why would he have said mass? Didn't have the concept of what atoms were. Okay? Without the concept of atoms being a physical single object that I can then build with, like Lego blocks, the only thing he can do is measure the mass of a whole bunch of them and say, this is what I noticed, that when I mixed 2 grams of hydrogen with 16 grams of oxygen, I got 18 grams of water. Right? That's all he could come up with. Okay? So those were the easily measurable things. That's why it was set up initially in mass. This is why Dalton came back and said, let's actually break this down and say that the things that made up that mass are indivisible pieces, known as our atoms and our elements. And that's where he came up with his atomic theory. So he refined that process to then go through and say, instead of mass, we're looking at the numbers of those elements in each of those compounds. Okay? How could we possibly measure all of this mass stuff? Okay? You can do things like heat, because I thought that was kind of bizarre. How did this guy, long dead guy, figure out that everything had the same mass? The example I gave was hydrogen and oxygen. Why would that be a weird one to measure? They're gases. It's not easy to run gas phase stuff, so how would we figure that out? Okay? That's where we can go through processes like what you guys did in lab. We can add heat. Compound potassium perchlorate will decompose into 2 things, okay, when adding heat. I can measure those things. I can trap the oxygen gas and get the mass. I can trap the potassium chloride as a solid, okay, and I can see how that changed. And I can change the amounts of potassium perchlorate I start with and notice that I get the same ratios at the end as far as mass. Okay, so it's kind of a neat observation. Hydrates do something similar. Okay? Hydrates is water embedded in the crystal structure. Salt shakers, right? You've seen them? Anybody lived in a humid environment? Yeah, and they keep those maggots inside those salt? Yeah, they weren't maggots. You mean what?
Rice.
Rice. Why would you keep rice in a salt shaker?
Because rice also the moisture.
The rice will absorb the moisture in the humid environment instead of
The salt.
the salt. What would happen if the salt absorbed the water? Well, then it becomes a liquid, and you can't pour liquid in. Does it become a liquid? No. What happens when the salt absorbed the water? It created clumps. Water is present. I didn't change the phase. Water is now incorporated into the solid crystal structure, creating larger chunks. Salts will do this. They will absorb water but stay crystalline. But they absorb water in very careful ratios. That's the hydrate lab that you guys do in 3 or 4 weeks. Okay? Electrolysis, we can force electricity into molecules to see how things change. We can look at combustion. I can take an organic molecule, I can react it with oxygen, and I can look at the decomposition products that come out of it. This is just kind of a neat thing. These are observables. You won't get tested on this. Sorry, for those of you writing notes. Okay? So, Dalton refined it. Okay? You guys did very well with that Dalton question. The first 2 are the only ones that are false now. Why is the first one false?
Because we know that some stuff like atoms now.
Okay, we have subatomic particles. We have electrons, protons, and neutrons. Those are smaller than our atoms. Why is rule 2 false?
We got different electrons.
We could have different electrons on an element, making a different charge species. Okay, sodium metal kills me. Sodium ion allows me to live. All that changed? 1 electron. Not even 1 element, 1 electron. Okay? We went from sodium with its full valence to sodium ion missing an electron. I change 1 electron and I go from being alive to dead. Okay? And very quickly. Don't eat solid sodium. Okay? That will kill you painfully and fast. Okay? You can watch videos on it. They throw sodium blocks into water. Yeah. The big massive explosions, that's happening inside you if you did that. Don't do that. Sodium ion, on the other hand, allows all your muscles to function properly. Okay? So a very subtle change in the structure changes drastically the chemical properties. Okay? Where else or how else are atoms not identical? This was the most common answer, actually. Most people did not say charge. The number of neutrons. If I change the number of neutrons, I've changed the mass. I have different isotopes. Those now have different physical properties. One weighs more than the other. Okay? The rest of his rules fell out to be true, okay? Because they were a little bit more general. Okay? So now what we're talking about doing is taking these things. We've taken a bunch of content from over several hundred years, and we now put it all together to make reactions. Okay? And there's certain rules within our reaction systems. Okay? First and foremost, do we write out the names of the compounds? No. Why not? What's that?
That takes too long and we don't get the exact concentrations.
That would take too long. Okay? So we don't write out the names. Instead, we write out their symbols. But in the process of writing out their symbols, we have to make sure that their symbols correctly balance. You mean to go from the names to the formula, I have to know nomenclature? Yes. Okay? Not only that, I also have to specify their phases. Some of the phase information would be specified in the text. Sometimes you have to know what it is. Okay? So we've got our expressions. Okay? The next part is these are very much the same as mathematical expressions. Okay? Mathematical expressions are a little bit easier to deal with, okay? But they're ultimately the same. So let's try it this way. What is 2 plus 2? 4. What is sodium hydride plus acetic acid? You gave me 2 plus 2 equals 4 in like split seconds. Why aren't you giving me that answer in the chemical equation that fast?
We don't have something like that memorized.
You don't have the practice and skill behind that. That practice and skill comes with practice and skill. If I ask 2 plus 2 to a 2-year-old, they're about the same amount of time as you are with the chemical expression. Okay? It takes practice to develop that skill. That's what you need to work on to get the proper equation. Is there another answer? Did it have to be 4? You're like, yeah, of course it's 4. No? What do you mean?
1 plus 3.
Why pick out 1 plus 3? We start with 2 things, we end with 2 things in our chemical reaction. We don't always do that. We could potentially end with just 4. Okay? The chemical reaction is just the integers in your expression. And depending on what we're looking at and how the chemical reaction occurs, the identity of what those integers are may change. Kind of make sense? Okay. Whoops. Sorry. So let's do a couple more examples. 2 plus 2 equals 5. This is a trick question. I never asked. It's 2 plus 2 equal to 5. No, why does it not work? It's unbalanced. So what do we have to do with our chemical reactions? You have to make sure they balance out. They have to equal each other. That reaction arrow is inequality. So when we set up our chemical reactions, we have to make sure they balance. Okay? If they don't balance, it's just like writing 2 plus 2 equals 5. Okay? One more quick example on that. Oh, actually, no. Let's do this. Right? Still 5. You're like, no, that's wrong. I'm going to fix it. Is that now true?
I mean, yeah.
Yeah. Can I do that in a chemical expression?
No.
No. Why not? Remember what's happening. I'm mixing 2 things to make 2 things. Can I mix a negative of something? No. That would say it's less than its existence. Okay, I can't have less than its existence because these are physical things. Okay? Could I make less than its existence? Okay? That one you might, philosophically maybe, no. No. Which means when we go to a chemical expression, the mathematical operators that we're always going to use will be positives. Always, always positives. Chemical expression always gives you positives. We don't get the mathematical equivalent with the negative. Okay?
I have a question. Does it matter if it's solid versus gas with the states?
Do the physical states matter? Yes and no. Okay. Yay! In this class, are you required to specify the physical state?
Yes.
Yes. What is the name, for those people at home, this guy? What is the name for that compound? Okay. Hydrochloric acetate is going to be a problem because chloric is chlorine. Okay. So where you're going is hydrochloric acid because it's an acid. How do you know it's an acid? It's not just that it's an H, because if I jump all the way to H2 at the end, is that an acid? No. So what is it that makes it an acid? H and AQ. Do the phases matter? Yes. Because the phase allows me to name this as an acid. If I get rid of that phase, that changes the naming of the species. Okay? As far as you're concerned. Okay? So you're only expected to predict certain phases. And sometimes. Not all the time. But you are expected to predict those in some cases. Okay? If I just said sodium hydride, what's the phase? I wouldn't expect you to know that. Okay. If I said solid sodium hydride, how would you write that name? NaH, parentheses S. Okay, you would not write, just for clarity's sake, NaHS. Why not? That looks like sulfur. So we have to include those parentheses to make sure it's separating it a little bit from the chemical formula. Make sense? Okay? So how do we go through and balance the chemical reactions? Okay, well, we'll balance the chemical reactions by changing the coefficient in front of each of the species. Okay? So we went from, oh, it's just 2 plus 2 equals 4, or 2 plus 2 equals 1 plus 3, to now 2 times something plus 2 times something equals 1 times something plus 3 times something. That just got significantly more complicated, right? Okay. Are you responsible for that extra level of content? Yes. Okay. And this is where chemistry takes algebra to a whole new level. Algebra, we deal with how you solve complex equations with x's and y's and z's. Okay. And now what we go through and do is our x's and y's and z's, x is HC2H3O2, aqueous. Okay. That's now a single thing. How does that single thing relate to all the other pieces in the expression? Okay? So it becomes significantly more difficult to process those. With practice, you can see the parallels. Okay? So how do we go through and deal with balancing? Here are the rules that I would recommend you follow on balancing. Okay? I don't think these are necessarily any different than any other system. These will apply if you have to move on through 151 and 152. These are the same rules. 152 messes with some stuff in the middle there. Okay, 152 adds some extra stuff that makes it a little bit more difficult. I probably put it in the wrong spot. Okay, but they add some extra rules there. We will look at an alternate way of balancing equations a little bit later this semester. Okay, for very particular equations. Okay, the biggest thing with balancing equations is that you will always know you're right. Okay? Because 2 plus 2 equals 1 plus 3. How many of you are going to get that wrong? Oh, that's right. You should keep your hand down. You're right. None of you would get that wrong. It's like, why is no one raising their hand? How many of you would get that right? That's a little bit better. Okay, so at least we got 3/4 of the class getting 2 plus 2 equals 1 plus 3. Okay, that's a step up. The rest of you just were like, I don't want to answer. Okay, you can check your work. Okay, and when we go through and balance, which I think I might have done in the video, this check your work thing needs to happen so frequently that you literally get angry at me. I want you to check your work so often you're like, Mike is just a jerk for making me do this. Okay? Because that emotional trigger is, guess what? Going to do what? It'll help make you do it, but it'll also make you remember the whole process. Okay? So we got to walk a fine line. I constantly want people to think I'm a jerk because now you get emotional about the content and you remember it. But I don't want to be that much of a jerk that you now hate me and you don't do the content. Okay? So we're bouncing back and forth on that. Okay? So, which of those do you want to look at?
The long one.
The long one.
Because it's the, yes.
Because it's what?
Because it's the long one.
Oh.
Okay? Because you all watched the video, you all saw how to do this. Okay, we're going to do it two ways. We're going to go method 1 up and method 2 down. Okay? Method 1, where do I start? I'm going to balance aluminum. Notice in my work I'm starting right above the equals arrow. And I'm trying to compare across that equals arrow how much shows up on each side. So on the left-hand side, how many ALs show up? 2. On the right-hand side, how many ALs show up? 1. With only 1, these don't balance. They must be balanced. So what can I do? I can put a 2 in, so it'll become AL2 and O3. No, why can't I do that? I'm changing the chemical identity. When we get to balancing chemical equations, you cannot touch the formulas. Those formulas are the chemical identity. I can only change the multiplier on the entire expression. So I could put a 2 there. Okay? Now what happens? How many aluminums on the left? 2. So now what do I move to? Okay? I did hear somebody suggest something else, but we're going to go to BA first. Sorry to that someone else who was over there. How many bariums on the left? 1. How many bariums on the right? 1. Is that balanced? Yeah. Okay. Now what do I balance? Okay. That same person on the right, I'm going to ignore you again. On the left I heard sulfur. How many sulfurs on the left?
3.
Okay. Isn't there a 4 in there? That 4 only applies to the oxygen. The 3 applies to the parentheses. There's 1 sulfur in the parentheses, but there's 3 sets of those parentheses. The sulfur is 3. On the right, 1. Does that balance? No. What do I need to do?
3.
Okay. I need to put that multiplier in there. Okay. Again, it's a multiplier. It has to go out in front. Okay. This is where I see most students kind of freak out because they go, oh my God, I just balanced barium and it was 1 to 1. Let me go back and do that. No, leave it alone. Don't touch it. Okay. Finish your work, then you can worry about it later. Okay. What's the next thing you want to balance? I noticed the right side stopped suggesting that. Okay. Nitrogen. How many nitrogens on the left? Yep, you're right. Sorry. For the same reason for our sulfur. On the right? No. 6. Who said 6? Why? I have 3 nitrogens within the unit, but I have 2 of those units. So I've got 6. Is 2 equal to 6? No. What do I need to do? I need to put a 3. Where do I put the 3? In front of the BA. There's already a 3 in front of the BA. Just checking. Okay. Now what do I do? Okay. No, I do not go back and balance the bariums. I should move to the oxygen because the oxygen is the last element to go through and balance on this. How many oxygens do I have on the left? This gets fun. There's 4, but there's 3 sets. That gets me 12. There's 2 with the 3, which gets me 6, but 3
So 30.
gets me 18. 12 plus 18. I thought you were trying to tell me 3 times 6 was that.
Oh, no.
30. 30. I should have listened to you. Okay. If we go through and do the other side, 3 and the 3 gets me 9, because there's 2 here. This takes me to 18. I heard a 6 for the 3 and the 3, just to kind of clarify that again. There's 3 within the parentheses, but there's now 3 of those parentheses, which becomes 9. 3 times 3 times 3. Saw a face on the left. Are you okay with that? Yeah? Okay. No. It just looked like you were looking at me kind of disgusted like. Trying to make sure it wasn't, like I screwed something up. The next one.
12.
The 4, but then I have the 3 and I get 12.
Which is 30.
12 and 18 is 30, which is balanced. Okay, now what do I do? I have to go through and erase all of this work because all of that work was work to get those numbers in front. Sorry, my eraser's kind of small. And I forgot there's stuff underneath there. And now what do I do? Aluminum on the left. 2. Why 2? On the right. 2. What do we do next? Was it barium? Barium, which I think I had in purple. How many bariums on the left? 3. On the right? 3. Then we got sulfur. I don't even know what color that was. What were the numbers? 3 and 3. Nitrogen. 6. Sorry, I'm getting lazy on the colors. And 6, I believe you. Oxygen.
38.
30 and 30.
Oh, that's quick.
That was quick because I just cheated and wrote the numbers down. Sorry. You should do all the math. Okay? Now what do you do? They were all good, right?
Right?
No, remember Mike's a jerk. Do it again.
Do it again.
Do it again. Okay? Now after you've done it that time, what should you do? You do it again. Okay? I want you to do it again multiple times or not right this second, but when you're doing your homework. I want you to cycle through those multiple times. Okay? So that you get used to it. So that you've built that pattern. You know what you're doing. Okay? So that when you get to the exam, how many times do you have to check it? Once.
I have a question. Can we do, you know how you split up sulfur and
Were you my nitrate or my sulfate?
can we do it like SO4 and
Was there a second method? I said I was going to do method 1 up and then method 2 down. Let's see. Can I go back to leave all my work in there? Oh, go back. Other way. There we go. Cool. There's all my work, right? Okay, that was method 1. What's method 2? What am I going to start with? Aluminum. Okay, I'm going to erase those numbers because, right, we're working on that. We're saying method 2, so we don't have any of that information to help us out. Okay. We go through and look at aluminum. How many aluminums? 2 and 1. So what do I do? 2. This is not looking very different. This is kind of silly as a second method. What are you suggesting makes this different?
do SO4 instead of sulfur and oxygen?
Why can you do that?
Because it's
Did SO4 change in the course of this reaction? No. The amounts changed, but that's what we're trying to balance. SO4 itself did not change, just like Al did not change. I can balance complex ions as their own unit. So now when I look at SO4 on the left, how many do I have? 3 SO4 on the right. 1, how do I balance? 3. Now I could probably move to the barium. Was it 1 and 1? The 1 and 3. Okay. That's kind of interesting. Because we didn't get that last time. Remember barium came out at 1 and 1 when we balanced it out? Okay. So it's not balanced. What do I need to do? Put a 3 in front of the barium. My 1 becomes a 3. Now what do I balance? Now I'll balance my NO3 on the left. I have 2 NO3s, but I also have 3 of those sets, so I get 6 on the right. 6. Now what do I do?
Check it.
Check the work. Make sure it's all right. Right? What do I notice happens? It's balanced. Was that the same answer I got as above?
Yeah.
No.
No.
Yeah, it was.
But you have to balance your absolute to the bottom.
Oh, I didn't fix that, sorry. I noticed that I did it for one, but then not the other. So yeah, because 3 SO4, I just didn't fix my one. So is it balanced? Yeah, we get the exact same answer. Which is easier? Look at those numbers. 2, 2, 3, 1. That became a 3. That was a 6. All those numbers I can count on my hands, right? 10. What's the problem with the one above? 30. Is that a really hard thing to count up to? Yeah. Okay, which one's easier for you? That's on you. You get to decide which one's easier. If you like the second method, then do the second method. If you don't like the second method, you can do the top one. Most people find the top one difficult because the oxygen, you're splitting those complex ions and they show up in multiple different places, and it can become challenging to balance that. Okay? So that's why most people avoid the first method. Okay? But I didn't want to do that. The bottom one, we have hydrogen and CO3 is carbonate. Good. Okay, that's a complex ion. Can I balance carbonate on both sides of the equation? Why no now?
They're different elements.
CO3 as carbonate does show up on the left. Does CO3 show up on the right?
No.
No. What does that mean I have to do? I'm going to have to separate them and balance them out as the elements. Okay, so as long as they don't change across the equation, you can keep them. If they do change, you got to balance out element-wise. Make sense? Yes?
Are you going to do the C4H10 plus O2?
It's not on the next slide. It's somewhere in there. We will eventually get back to that. I would argue that's less important. Okay. And for those of you that didn't watch the video, there was a combustion reaction in there that's difficult to balance. It is exceptionally difficult to balance. You'll probably see it maybe twice this semester. You've already seen it once in the video. Maybe you'd see it as an extra credit question or a multiple choice once. Okay, that type of balancing, because it's trickier to deal with. Okay, chemical reactions. You're responsible for, how many is that? 5, technically 6, because I forgot to include the combustion on this. Okay, you're responsible for knowing those 6 chemical reactions. Some of them you're responsible for knowing more details about, like phases. Okay, some of them you're not. Okay, so the first 2, combination and decomposition, those are just bulk patterns. You're not expected to predict the products or predict reactants or any of that. Okay? You're just expected to look at a chemical reaction and go, that is a combination. How would you know it's a combination? I start with 2 pieces and I get 1 piece. So let's look at a quick challenging example here. How many pieces do I start with? Anyone want to hazard a guess at 3? I'm not missing an oxygen. That's actually fully correct. There's 2 H2s, so isn't that 3 pieces? In our combination, all we're referencing is the individual units, not the amount of individual units, but the individual unit. There are 2 units in that expression, H2 and O2. 2 units, or 2 pieces. Okay? I can change the number of the pieces. That doesn't change the chemical reaction. That is still a combination reaction. I took 2 pieces and I put them together to make 1 new piece. The specific amounts of each of those pieces is the balancing the chemical reaction aspect. Okay? In all of these examples, none of those are strictly balanced. Okay? We're using A, B, C, and D as generic labels. Okay? Those don't correspond to any element or complex ion or any of that. Okay? So there's no strict amounts in each of these. The decomposition, well, if I decomposed, what would it look like up here?
Oh,
Disgusting. Why would it be disgusting?
be a gas and different parts.
I'd have different parts. My arm just fell off. That's That's a neat sound effect for that. Right? There's different parts of me. I disassembled into larger pieces. That's a decomposition. Okay? Does it have to be only 2 pieces? No, it can be tons of pieces. Ultimately, it doesn't matter. But I'm starting with 1 piece and I end with multiple pieces. Okay? Single replacements. What's happening in the single replacement? I'm swapping. Okay? And I'm only swapping 1 thing. Okay? Me and my girlfriend, not so great. My wife, pretty cool. I'm going to swap that out. Okay? In a history context, don't be like, I have a girlfriend now and a wife. Come on. Over time. Jeez, you people. Okay? And see, I'm the C because, I'm the C because I'm the average one, right? And they're better than me. See? Is that better? You happy with that? Okay, double replacement, what's happening? Okay, I'm not bringing, I already started, I gotta do it. I think my friend's wife is cooler than my wife. I'm gonna convince him we should swap. Okay, this is a full swap. Okay, couples. Single couple. Does that make sense? Yeah, those were horrible examples. I hope my wife doesn't watch these. Okay, neutralization. Anybody notice something interesting about neutralization? In the first piece, how many things do I have? 2. Second piece. 2, because OH is a complex ion, that's a single unit. So in a neutralization, I have 2 things and 2 things mixed to make 2 things where what happened? They swapped. A neutralization is a double replacement. Why would I call out neutralization as different than double replacement? What's the difference between those 2? I'm being very specific in the neutralization what's there. I'm saying H is there in one species, and I'm saying OH is in the other. To give you an extra little bit of hint here, typically for that one, you would also see an AQ written there. What is that species? An acid. Why do we call out neutralizations as separate from double replacements? How many of you heard about acids prior to this class?
Yes.
It is the most common chemical reagent out there. Most of general chemistry is focused on the acid-based chemistry. Right? We call it out as a separate reaction because historically it is probably the oldest chemical reaction. Okay? So it has some kind of historical significance. It's super common. Virtually all of second semester general chemistry looks at that reaction, okay, in gory detail. Okay?
Is there 6?
There's 6 because you get the combustion, which isn't on that list, and I always keep forgetting to put it in there. It will show up as a slide later. Okay? We got a little bit of time, so we'll look at some examples. Combination reactions, right? This is from the video. I didn't do all of these. You'll notice that there are 3 combination reactions listed here, different colors here. Those are giving you context about the types of combinations there are. You are not responsible for predicting the product of a combination. You are responsible for using the textbook to see what the product of a combination may be. Okay? So under those circumstances, you can predict what's going on in these. So if I take magnesium metal and react it with oxygen gas, solid plus oxygen gas, why is it O2? It's a diatomic element, so I have to specify it as O2 to make what? Magnesium with oxygen. Don't worry about the phase. Okay. Should I balance the equation yet? Yes. Why?
It's not because you all the elements.
When we predict products, we have to make sure the product we predicted was correct before we balance the equation. How would I know that product is correct? What kind of compound is this? What kind of bond is between magnesium metal and oxygen non-metal? And ionic. Are you responsible for being able to balance ionic compounds? Yes. What is the charge on magnesium? A +2. How do you know it's a +2? You're required to have that memorized or recognize how to get it on the periodic table. Oxygen, same deal, it's a -2. Is that formula correct? Yes, because that formula is correct, now I can balance the equation. Okay, and in going through to balance that equation, we'll notice 2, 2. We'll pick up, we'll probably pick up there and skip over the kind of calculation stuff. We'll shift that later in the semester, or later in the unit. Okay, so we'll pick up there, whatever.